So we were discussing regarding the analysis and how to find out the maximum amplitude and the frequency, and if there is the natural frequency and if there is any resonance, so that we can prevent those in the machine foundation. So we stopped here. So we have this system. So just a quick revision of the previous class. So we have this system, we have this force F naught sine omega t, and we have the force from the spring and the mass and despot kz plus c into the velocity. So we have the force in this direction. So the total force, if we sum it up, so the total force is summation of the forces is kz plus c into velocity minus F naught sine omega t. So that is equal to the mass into acceleration. So we have F is equal to ma. So this is the basic equation of the motion of the mass here, which is acted upon by a vibrating force of F naught sine omega t. So we saw that we are not concerned with this damping effect because at higher frequency ratios, so frequency of the operating system by the natural frequency of the system, if that is at a very high ratio, we see that the effect of damping is very less in the system. So the amplitude is not affected much, or the magnification factor is not affected much by the damping. So at higher frequency ratio, it is almost negligible. Okay, it is almost negligible. So that is why in our cases of analysis, we generally neglect the damping force. Okay, so what will happen if this force is reduced? So the phi angle will reduce. So F will reaction will move in this direction, and the applied phase will come in phase with the acceleration here. Okay, so ultimately we will have the force from the system and the applied force. So that is what the reduction in the damping effect, damping force it does to the system. So the force, it moves in phase with the acceleration here, and the resultant it will move on to here. So the angle phi will reduce. So basically it will be like this if the c reduces, or if it reduces way too much, it will be of this sort. So it will move in phase. Okay, so as the c reduces, so this component will reduce, this component will reduce, and the resultant will move up. Okay, and it will be in phase with the acceleration. And of course, if there is resonance, we saw that the result, the applied force, it it attains a phase difference of pi by 2 to the system. All right, so the acceleration component, and if there is no damping, then thing is that there is infinite displacement occurring in the system. But what happens is that when there is a damping, so the damping reduces the maximum amplitude. So with increasing damping, the amplitude reduces, so the magnification factor reduces. Okay, so so the things to note for is that before going into the further discussions, so we will just have a quick recap on the soil properties. So we have the coefficient of elastic uniform compression, that is Cu. So we have the coefficient of elastic uniform compression. So that is Cu. So Cu is uniform compression. So uniform compression by the elastic settlement. Alright, by the elastic settlement. So that is what is the coefficient of elastic uniform compression, and we saw that we can obtain this using the cyclic plate load test or the block vibration test, vertical block vibration test. Then we have the coefficient of uniform elastic shear, okay, and we can relate that to the spring constant. Alright, so Kz is equal to Cu into the area of the foundation. Alright, so that is Kz. So similarly, we have the coefficient of elastic uniform shear C tau. Alright, that can be obtained by doing a horizontal block vibration test. So that is related. So that is uniform shear by. So uniform shear by elastic shear strain. Alright, elastic shear displacement. So elastic shear displacement. So similar to this, we can relate the C tau with the horizontal stiffness in the block foundation. Okay, so in that case, so when the block is moving in the horizontal direction, so we can relate that to the Kx or Ky is equal to C tau into A, where A is the area of the base of the foundation. Okay. Now there are other three coefficients. So we have the coefficient of non-uniform compression and non-uniform shear. Okay, so it is a bit difficult to obtain. So there is some correlations given by IS code. Right? So there is correlations given by IS code. So CU, so IS 5249, the IS code 5249 gives the correlation between Cu, C tau, C phi and C psi. Okay. So emphasis is mainly on this two, determined using in situ test. Okay, in situ test, that is what we do. So thing is that Kz is equal to Cua and Kxy is equal to C tau into A. So C tau is the coefficient of uniform elastic uniform shear, and Cu is the coefficient of elastic uniform compression. So we were discussing regarding the displacement of this system. So we discussed that there are four modes of displacement. So there are 6 degrees of freedom and there are 4 modes of displacement of a block vibration. Okay, so we have this system. So if we want to find out what is the First of all, let us write the equation of motion. So we have F equal to ma. Okay, we start with that. So what is F? Alright, so F is actually the summation of all the forces. So if we consider this mass here, so we have P naught sine omega t. So we can consider here P naught sine omega t, or we can consider also Px to not cause any confusion. Okay, so this is Px into sine omega t. And we have the k into the displacement. So when there is a displacement, so we have the displacement k, suppose we can say z, into the displacement z. So at any time t. Okay, z at any time t. So we can say here k z into z, small z, that is, okay, small z, minus pz, sorry, so this is pz. So pz sine omega t, so equal to mass into acceleration in that direction. Okay, so again we know omega n in translation in the z direction, so that is equal to root over kz by m. Okay, so ultimately we have kz is equal to, we can write kz is equal to omega square, omega n tz square into m. Okay, so this is what we will write here. So at the maximum displacement, so at suppose we have at the maximum displacement z, right, at the maximum displacement amplitude z a, suppose, so this is the maximum amplitude. Okay, so that is the maximum. So if this is the equilibrium position, so it will move up to the maximum position z a, and then it will come back and it will go to z a. So at this position, so we have pz, the maximum force. Okay, so here we have omega square n t z square into m into z a, that is the amplitude, minus p z, that is the maximum force at that point. Okay, so that is equal to the maximum acceleration, which is given by m omega square z a. Okay, so if we again move this pz to this side and this one to here, so we will ultimately have, so we can now za we can take common, so we have omega n tz square minus omega square is equal to pz. Okay, so ultimately we can find out what is the maximum amplitude. za is equal to pz by m, sorry, it is m, so here there will be m. Okay, so m into omega n tz square minus omega square. So za is proportional to the force applied. Okay, to the force applied, and it is inversely proportional to the difference. So the difference increases, the za reduces. Alright, but obviously the acceleration in that case will increase, but the za will reduce. Okay, the za will reduce, and if the operating frequency and the natural frequency of the system, they come to close to each other, and if it is almost equal, then ZA tends to infinity. Alright, so there is resonance. So that is, we have to prevent at all cost. So similarly, we saw that for the horizontal case, so here we have the, so here Kz is equal to CU A. Alright, so just as we have defined here, CU A. Alright, so in this case, we will have, suppose in the X direction, so X amplitude, similarly X amplitude in the X direction, that is. So this is the mass and this is the spring, and this is Kx and this is mass. So similarly like this, we will have XA is equal to Px, okay, by m omega natural in translation in the x direction square minus omega square here, okay, and Kx will be given by C tau into A, okay, and Kx and omega and Tx will be root over Kx by m, just as in this case. Only the in the previous case it was in the z direction, in this case it is in the x direction. Other things will remain same. So F equal to ma, we start from there. So the forces in this, so suppose we have the spring force here, so Kx into x minus Px sine omega t is equal to mass into acceleration in the x direction, okay, and here we have acceleration in the z direction. So ultimately we have the maximum amplitude. So here also, if the frequency of the system, and the operating frequency are close, so we have very high values of amplitude. So that is what we have to prevent. And of course the force, it also depends on the force which is applied. So now what we do, so up till now we have discussed about the motion, translation motion. So two degrees of, two modes of vibration we have considered. One is in the z direction or vertically up down direction, and one is in the left right or x or y direction. Both are same, okay, so x or y direction, whatever you consider, both are same. So both are mode of uniform shear, okay, so those two modes are already considered. So now what we will consider is, so we have the x and y, so we will consider the rotation about either x axis or either y axis, okay, so either x axis or either y axis, whatever you consider. So we will consider the rotation about y axis. So basically this is the x, it is written here, this is the x axis. So if it rotates in this manner, so if it rotates in this manner and this manner, so we will have the rotation about the y axis. Okay, so that is what we will consider. So thing is that first of all we have to obtain, so since it is non-uniform compression, so you can see that the compression is not uniform, so we cannot say that, as we said, Kz is equal to Cu into A. In this case we cannot say that, okay. So in this case, and in this case also, that is the, we cannot consider the force equilibrium, so the force equilibrium is not coming into play. Okay, so here in this case, since it is a rotational motion case, so we will consider the moment equilibrium first of all. Okay, or we will consider rotational equilibrium. So the mass rotates about the point O. Right, point O means the axis about O. Right, so we have this block, and we have an axis at O. Right, so this is O, and we have this axis. So y axis. So it rotates about this entire axis. Right, so it rotates about the axis at O. So now we have to find out the moments. What are the moments applied? So obviously one of the moments which is applied is my is equal to mo into sine omega t. Okay, so that is the maximum moment. Mo is the maximum moment which is applied, and about the y-axis, so we have, as we had the force function f is equal to f naught sine omega t. So here about the y-axis we have my about y-axis, the moment about y-axis varying with time, and mo is the maximum moment. Okay, sine omega t. So that is the maximum moment. So that is applied. So one moment is already there. Now thing is, as soon as the body, the block rotates, as the block will rotate, so this is the block center of gravity of this position here. So this is the center of gravity of the block of this position here. Okay. Now as it rotates at an angle of phi, so suppose it rotates at an angle of phi. Okay, so if phi is in ratio or radians, we can say, right, if phi is in ratio or radians, so we have this is L and this is suppose this is y and this is x. So phi is equal to y by x. So y is equal to phi x. Okay, so in this case x is equal to L. Okay, so we have y is equal to L phi. Okay, so I hope you could understand. When the mass will move, we have the center of gravity, and as the mass will rotate, the center of gravity will actually rotate to this position here. Okay, and this is the phi here, actually L phi. Okay, so I mean it is a small amount of rotation, so we can consider this position and this position to be same, and L phi to be the displacement of the center of gravity. Okay, so we have the displacement of the center of gravity by L phi. Okay, this is L and this is L phi. So the center of gravity was here and it displaces to here. So now we have the weight of the mass acting through this center of gravity. So we have a moment about this point. So if you consider the moment about A, so we have a about O, so we have a moment which is equal to W so we have a moment about the point O which is equal to W into L phi. So this is the moment about this point. Okay, so W into L phi. So one moment we have got. So that is because of the displacement of the center of gravity. One moment is already applied. My is equal to m naught or mo sine omega t, m naught sine omega t. So that is already applied, and we have one moment due to the displacement of the center of gravity due to the rolling or pitching action of the foundation. Now apart from that, what other moment will arise? So these two we can consider to be destabilizing moment. Okay, these two we can consider to be destabilizing moment. Now apart from that, we have the non-uniform part of the compression, which will now stabilize the motion. Okay, so now how to find that out? So two moments we have already had, so we will continue to the next one. So my is equal to m naught sine omega t. We apply due to the rotational motion of the center of gravity. Okay, the center of gravity is displaced, so we have the moment due to the displaced position of the center of gravity. Okay, so the moment due to the center of this one, so we suppose say mcg. Okay, mcg we have is equal to w into L phi. Now phi is a function of time, remember that. Okay, so phi here, so phi is a function of time, so phi is equal to phi naught sine omega t, right? And maybe there may be an alpha, alright, a phase may be there. Okay, we will determine what is the phase afterwards. So thing is that phi here is a function of time. Okay, so it varies with time, so it will, like a pendulum, tick tock tick tock tick tock, it will go on. Okay, so just like that clock that we had with the pendulum. Okay, so it goes in this manner, comes back. Okay, right, so tick tock, so it goes and goes. So phi will vary with time, so it is a function of time. So this moment is a function of time, as is this moment. So this is the maximum moment. Okay, so this will be phi max, so maximum of that will be W L into phi max. Okay, so that part you have to be, you have to keep in mind. So now let us find out. So these two are destabilizing, so let us find out now the stabilizing. So to find out the stabilizing, what we will do is, so this is an area of dA, small area. So what is dA? So if we have the block in this manner, and this is the axis of rotation, so dA is basically a strip here. Okay, so since the compression will be uniform at least in the y direction, so this triangle, it will be uniform in the y direction. That is what we have assumed. Okay, so we can consider this area as whatever is the length of the foundation into dx, suppose. So that we consider as du. So dA is equal to dx or dy in this case into the length of the foundation. Okay, so we will consider that as that strip as du. Okay, So now we know C phi is the coefficient of elastic non-uniform compression. This is the area dA. Okay, dA is, so this is dA. Okay, so we have the foundation here. We have the foundation here. Alright, and this is the axis of rotation about the point O. So this is the point O. And we have a strip here dA. Okay, so this area is dA. And point, at that point we have a reaction. So suppose this is the soil reaction, and that reaction will be dependent on how much compression this part is undergoing. So that will be, compression will be L phi. Okay, so suppose we consider this to be L. Alright, so this is length. So this is the length L. Okay, and this is the angle of rotation phi. Okay, so the compression in the here in this part is L into phi. Okay, so at that point the total force C phi into L into phi. Okay, so that is the ds. So that is the soil reaction. So I will just once again repeat this so that it becomes easier. So we have these two moments, my and mc g. So we have already two moments. So now we have to find out the moment of the soil reaction. Okay, so we have this axis y. Okay, we have this axis y, and the foundation, it rotates about the point O. So this is the point O. So we have a compression here like this, in this manner. So what we do is we take a strip of area dA at a distance L. Okay, from the axis of rotation. From the axis of rotation, we have at the distance of L, we have this area dA. Okay, now that is an infinitesimal area. So let the soil reaction at that point be ds. Okay, so we can consider that there are numbers of springs. So we have one spring there. So what we will do is, so we have numbers of springs. So the spring will be compressed in a different length. So this is one spring, so it will be compressed this much. This is another spring, it will be compressed this much. Then there is this spring, then this spring. Okay, so there is a motion here. So definitely the force here, the force at this spring will be proportional to the compression on this spring. So we are considering only one spring here. So we can consider that stiffness C phi. Okay, C phi. So the stiffness of the spring at that point is C phi. So what is the reaction ds? So ds reaction is, or we can say it to be, suppose, as the soil reaction, or SR. Alright, so we can say SR, suppose. So we can say that to be soil reaction SR. So soil reaction SR at this point. Okay, at this point. So we have SR at this point. So that will be equal to the compression in the spring into the stiffness of the spring. So C phi is the stiffness of the spring there. Alright, because it is unit area we are considering, infinitesimal area. So C phi is the stiffness of the spring, we can consider there, and into the multiplied by the compression at that point. So what is the compression at that point? So if the rotation of the foundation is phi, if the rotation of the foundation is phi and this is L, so we have the compression at this point to be L phi. Okay, so here we have different springs. Or we had all the springs in this manner. Initially we had all the springs in this manner. Okay, they were all in the same position. Then when the foundation rotated, okay, when the foundation rotated, the spring, they got compressed. So we have this uncompressed spring here. So at the center of the rotation, and from the center of rotation we have the compression in the springs. So the forces will vary from here to here. Okay, so at this point, at any point, suppose L, at a distance L, so we have the rotation phi, and we have the soil reaction at that point as R. So at that point, soil reaction as R will be equal to C phi into this compression, this amount of compression, that is equal to L into phi. Okay, if this is L and the rotation is, so this is L phi. So as here we have found out. Okay, so L phi. Now that is the per unit area. Okay, so per unit area, that is soil reaction per unit area. So this is C phi into L phi into soil reaction per unit area. So now the total force in this area of dA magnitude is, we have, is equal to C phi L phi into dA. Okay, so that is the total force. Okay, so that is the total force at this area now, at this area. And this is now how to find out the moment. So C phi moment about that area. So from this, that is from at this point. So the force at this point we have. So suppose this is uh, R. Okay, we represented this R, the total soil reaction at this area A. Alright, RdA we write. Alright, so C phi is equal to, we have I mean the moment about of this RdA is equal to, so RdA into L, we will have the moment, so into L. So we have the force C phi L phi dA at this point. Alright, we have the force at this point, and that force into this moment, into this lever arm, we will have the moment. Okay, so this one. So ultimately the moment from the force here will be C phi into L phi into dA. So that is the force into L. Okay, so this is the force into L. Into L is the lever arm. So that is the total moment from the area dA. So what is the total reactive moment from the soil? So mr is equal to, so we integrate this. So integrate about the whole area. So we have C phi L phi, L into phi, that is L into phi dA into L. Okay, so C phi and phi we can take it out. Okay, so we can take it out, the C phi and phi, because those two are constant at a particular moment. Alright, at that particular moment these two are constant, and we have to integrate about dA into L square. So L square. So if you see dA into L square, so that is the moment of the area. there is a moment of the area about the y-axis. So if we have the foundation in this manner, and we have the y-axis, and we have a strip here, all right. So dA into the radius of gyration, so this is L square, all right, square of the radius of gyration, so summation of the square of the radius of gyration. So dA, integrating dA into L square, we have I, all right. So that is the moment of inertia of the contact area, all right. So the moment of inertia of the contact area, so that is C phi into I, all right. So I is the moment of inertia of the, the base area of the foundation base area about this y-axis, okay, about this y-axis. So I hope it is clear. So thing is that, so first of all we have the area A, dA, the area dA, okay, and we have the rotation of axis y-axis, and we have a strip here, area dA. So we can consider that to be composed of springs, okay. So as there is rotation, we have compression in the various springs, okay. So initially the spring was like this, then there was compression here. So this is uncompressed, then the compression will vary with the distance from the center of rotation. So at this point, if this is L, the compression is L phi. So the reaction at this point is C phi L phi into the area. Okay, so area at that point is dA. So C phi into L phi is the compression into the area, that is dA. So that is the force. That is the force. So what is the moment of this force about this point? So that is force into the lever arm again. So this is the force into the lever arm. Okay. Then what is the moment of, what is the total moment? We integrate about the point, about this point, about the whole area. Okay, so here we can take out C phi and phi, and we have to integrate dA into L square. Okay, so this is the, so we have this radius of gyration L, alright. So dA L square integrating, we have the moment of inertia of the foundation area, for base area, okay, about this axis of rotation I, about this axis of rotation I. So that is, we have the moment of resistance. So we can say the moment of resistance, the moment of resistance from the soil is Mr is equal to C phi into the angle of rotation into the moment of inertia of the foundation base, of the base of the foundation about this axis of rotation. Okay, so that is the moment of resistance. So we have the three moments. One is MR, the soil, and the other two is applied. So MY applied and uh, MCG. MCG. Okay, so these two, if we consider positive, this will be negative. Okay, and obviously we will have the rotational, I mean, angular acceleration. All right, so we will have the rotational, I mean, motion. So we will have the angular acceleration into the mass moment of inertia. So that is the inertial rotational, I mean, inertial, I mean, moment. Okay, so that is of course, so applied moment equal to mass into the angular acceleration. Okay, so just as F is equal to ma, so we have applied moment, summation of moment is equal to mass into angular acceleration. What we have to do is we have to sum up the moments. Okay, so that is what we have to do. So we have three moments. One is the moment from the resistance of the soil, which is opposite to the applied moment, and moment from the displacement of the CG. My is equal to m naught sine omega t. So we know mr is equal to c phi into the I, that is the moment of inertia about the y-axis of the base of the foundation. So c phi is the coefficient of non-uniform elastic non-uniform compression, and phi is the angle of rotation. So that is the moment of resistance of the soil. Alright, so or moment due to the soil reaction, that we can say. So then apart from that we have the my, which is m naught sine omega t, and we have mcg, which we have w into capital L, that is this L, not this one. So this is small l, okay, and this is capital L into phi. So ultimately we can write the equation of motion. So we have the summation of moments is equal to mass moment, all right, or mass moment of inertia into the angular acceleration, that is, okay. So ultimately we have summation of moments about the y-axis equal to mass moment of inertia, all right. So we can say m naught, so about the y-axis, about this axis, right, the entire block. So this is the mass moment of inertia of the block about the axis passing through here, all right. So passing through O throughout the entire foundation in this manner, y-axis. Okay, so about that axis we have the mass moment of inertia. So into the angular acceleration we have the moments here. So that is analogous to F equal to ma, which we had. Okay, so that is analogous to that. So first of all we have the applied moment. So m naught sine omega t, this was, then plus we have in the positive direction we have this moment, which is equal to w into L phi, so w into L phi, okay, and then we have the moment of from the soil in the negative, rotation, anti-clockwise rotation. So that is minus, which we have found out is equal to c phi phi I, c phi, right. So summation of moment is equal to so we have m naught sine omega t plus wl phi minus c phi into the angle of rotation into the moment of inertia of the area moment of inertia of the base foundation base, that is. So is equal to m mass moment of inertia about that axis into the angular acceleration. Okay, so we can now again rearrange that into, so we have m into mass moment of inertia into angular acceleration plus, okay. Now if I take out phi, from this one, so phi into, so we are now on the other side, okay, so we are on the other side of the equation, so the signs will change, so this will be c phi and I, okay, so this is positive now because we are on the other side, minus wl, okay, is equal to m naught sine omega t. Okay, so I hope you could understand this step. So on the other side, so now thing is that, so now what we say, so we have this equation, so we have this equation, so mass moment of inertia into the angular acceleration plus phi into c phi I minus wl is equal to m naught sine omega t. Now if I again write it in this manner, so we have mass into acceleration, so plus k into displacement is equal to f naught sine omega t. Okay, so here you see this term is analogous to k, okay, and this term is analogous to m, okay. So mass moment of inertia you can easily find out. So if it is about the y axis, so about this axis, so it will be 1 by 12 mass into length square plus breadth square. Okay, so that you can easily find out. It is very easy to find out. So that is the moment of inertia about the axis. Okay. So moment of inertia you find out. So anyway, so this is moment of inertia. So we can find, so here we know omega n is equal to root over k by m. So here we have the natural frequency for the rotational motion. Alright, so rotational frequency for the natural frequency for the rotational motion. Now we have omega n phi is equal to, so root over now k. So k is c phi I minus wl. So that is k. And we have the mass moment of inertia, which is equivalent to the mass here. So we have mass moment of inertia. And similarly, so we have we had earlier defined, so ZA, suppose ZA, that is the maximum amplitude. So we have the force applied in the Z direction, maximum force applied in the Z direction, divided by mass into omega and square in the translation in the Z direction minus omega square. So this is the maximum amplitude in the Z direction. So similarly here also we will have the maximum angle of rotation phi a, suppose, or phi a, yeah. So maximum, that is phi amplitude. So maximum angular displacement. Okay, so maximum angular displacement. So we will have m naught. So m naught is the applied force here. So m naught by, so in case of mass here, so we will have the mass moment of inertia. Okay, and we will have the natural frequency phi square, which is this one, minus omega square. Okay, so this is the mass moment of, this is the maximum angular amplitude. So here I you can also obtain. So I is it will be equal to uh, so I will be equal to BAQ by 12, I think. Yeah, BAQ by 12. So that will be the area moment of inertia about this axis. Okay, that will be the area moment of inertia about this axis. So I you can find out, and mass moment of inertia also you can find out. Okay, so not a very tough job. So mass moment of inertia. So ultimately we can find out what is the maximum angular amplitude. Okay, now in practical cases, so in in the most, applied cases, so WL, so basically L actually, so uh, so WL actually, in case this C phi I, it is significantly higher. Okay, in actual cases C phi I is significantly higher than WL. So WL we can neglect, right? Though it is there, we can neglect. So in that case we can approximate this natural frequency to be root over C phi into I by mass moment of inertia. Okay, so in that case, so as you see, the k, we can write k is equal to C phi I. All right, so k phi we can write it as C phi into I. Okay, so kz we have obtained Cu into A, kx or y we have obtained C tau into A. Okay, but in case of rotation we have k phi, the rotation is equal to C phi into the moment of inertia of the area moment of inertia of the base of the foundation about the axis of rotation. Okay, so that is the non-uniform compression motion. Okay, the modes of non-uniform compression motion. So now we have the yawing motion. Okay, so we have discussed three modes of vibration. So one is vertical translation, one is horizontal translation, one is rotation about x or y axis, so pitching or rocking, and now it is yawing. All right, so yawing we have to find out. So similar to whatever we have discussed, so here, so yawing also we have a moment, so mz. So what we can write is, so first of all we can write, so the moment mz, so we have mz into sine omega t, that is the applied moment. Okay, and if we have the angular rotation, so we have suppose an angular here rotation here, so this is alpha, so this is the angular rotation. All right, so we have the mass moment of inertia about the z-axis as here, so mass moment of inertia about the y-axis about the point O. All right, about the point O, so this is the mass moment of inertia about the y-axis about the point O. Now here we have the mass moment of inertia about the point, about the z-axis, that is, okay, about the z-axis, and that will be into the angular acceleration. Okay, so if this is alpha, so we can write angular acceleration. So similarly this one here, angular acceleration. Okay, and as we have written here, now here in this case we see that the CG is always on this axis, so it is rotating about the CG. Okay, so the CG is always on this axis and the rotation is about this axis. So this term, this moment will not be there, so we will have only this component. Okay, so we will have the polar moment of inertia about the z-axis. So we have, so in this case we had c phi, all right, I, so now we will have c psi, so that is of non-uniform shear. Okay, coefficient of elastic non-uniform shear. Okay, and then we have the polar moment of inertia z about the z-axis, and we have the angle of displacement alpha. All right, in this case, so angular displacement alpha. So alpha is also a function of time. Okay, so alpha is equal to alpha naught sine omega t, or plus some, phase difference. Okay, so some phase difference will be there, so you can take the symbol. So c phi and polar moment of inertia into the angular displacement, so that is equal to the applied moment. Okay, so equal to applied moment mz sine omega t. Okay, so here we can directly see that this is equivalent to k psi. Okay, so this is equivalent to k psi, so k psi is equal to c psi into polar moment of inertia about the z-axis. So we can if there is uh, this axis, and we have, suppose this is if I say suppose length, if this is length and this is breadth, okay, then about this axis we will have I equal to, or J equal to, whatever you can say, the polar moment of inertia is equal to 1 by 12 m b square plus L square. Okay, so that J polar moment of J theta you can find out. Okay, so polar moment of inertia you can find out. So we have the equation of motion now. So we have the equation of motion. So the equation of motion is mass moment of inertia about z-axis into the angular acceleration plus c psi into j about z-axis, all right, into the angle of into not psi, so we have the angle of rotation alpha, okay, equal to mz sine omega t. So here k psi is equal to c psi into polar moment of inertia, right, of the foundation base area, that is. So this is z, this is the polar moment of inertia of the foundation base area. Okay, so that will be without the mass, sorry, so that will be without the mass. So this is the mass moment of inertia, this is the polar, the area moment of inertia about the z-axis of this area, okay, of this area, that is. Okay, so similarly we will have the natural frequency we will have the natural frequency which is equal to by not mz, actually mz, okay, and we have the maximum angular displacement. So the maximum angular displacement, that is alpha, maximum alpha max, alright, or alpha a, we can see alpha amplitude. So in that case alpha amplitude will be equal to, so the applied moment mz, maximum applied moment mz, maximum applied moment mz by mass moment of inertia about the z-axis into omega and psi square, so this value minus the operating frequency omega square. Okay, so that is how we calculate the individual modes of vibration. Okay, so up till now we are discussing only the individual modes of vibration. Now thing is that it is not always that straightforward. Okay, so when there is pitching and sliding, so it is always in relation to each other, all right. So there is, coupled, so pitching and sliding, they generally always are with each other, along with each other, so we should always consider the two simultaneously, all right. So thing is that what we will do is we will now join the rotational motion and the translational z, okay, and we will simultaneously consider the rocking, okay, and the sliding, and the vibration. Okay, so we cannot consider this moment because this is out of this plane, so we will only consider whatever it is within one plane. So xy plane, at any xy plane, whatever the forces are there, we will consider at one xy plane. All right, so to be simplified in the calculation. So three-dimensional, we are not going to assume the calculation. We are going to consider whatever the forces, whatever the moments are there in one plane of action. Okay, so one plane. So we have this sliding in the x direction in this xy plane. So sliding in this direction we are not considering. Okay, so sliding along z, or translational motion, up and down motion along the z axis, it can be included within this plane. And the moment, that is the rocking motion about this plane, can be included. Okay, so we are going to include that. So that is vertical vibration, number one. Okay, vertical vibration. Number two is the sliding motion, sliding vibration, and number three is the rocking motion. Okay, so in the xy plane, or xz plane, sorry, xz plane. Okay, in the xz plane. So we have in the xz plane. So up till now we have considered the motion separately. Okay, so now we are going to couple or whatever there is in the xz plane. Okay, so this is the x-axis and this is the z-axis. So first of all is the number one is the vertical vibration up and down. Okay, so along z-axis. Number two is the sliding motion along the x-axis. Okay, so along the x-axis. And number three is the rocking motion. Okay, so rocking motion about the y-axis. So the y-axis is a point here. So this is the y-axis. So this is the y-axis. So it will be a point on that plane, on this plane. So about that point, so the rocking motion. Okay. So that is what we are going to consider simultaneously. So first of all, let us consider. So we have the displacement in the vertical direction. So we have the displacement in the vertical direction z. Okay, displacement in the so this is z, this is z. Then displacement in the horizontal direction, sliding, that is, okay, sliding displacement. So the point O was here, so it got slided up to this point. Now rotation has been shown in a magnified manner. It does not rotate in this manner, so only a small amount of rotation will be there. So sliding will be in this manner. Okay, we can consider the sliding to be in the same line here. So we have the sliding x naught at the base. Okay, and the rotation, definitely we will have the rotation. So we will have the rotation which is phi. So this is the angle of rotation. So this is the angle of rotation phi. Okay, this is the angle of rotation phi. So ultimately we will have now, so now we are considering all of these forces together. So we will have three equations of motions as we have discussed in the previous case. So one is the summation of forces in the z direction, sorry. So all the forces in the z direction we will sum up. So that is one equation. So that is equal to, will be equal to the mass of the foundation system into the acceleration in the z direction. So that is one component of motion. Then the other component of the motion will be, translational motion along the x-axis. Sorry, along the x-axis. So Fx is equal to again mass into acceleration along the y-axis, x-axis. Okay. Again, similarly, we will have the rotation. Now, rotation about the y-axis, that is. So summation of the moments about the y-axis. Okay, summation of the moments about the y-axis. So that we will have. So this we will have mass moment of inertia about the y-axis into the, so if this is phi, okay, so d phi by dt we will have the angular velocity, and d differentiating angular velocity with time, we will have acceleration, angular acceleration. So mass moment of inertia about y-axis into the angular acceleration. Okay, so that these are the three equations of motions, equations of equilibrium that we need to consider. So now we have to again isolate the forces and the moments. So if this is Z, so the soil will give an upward force. Okay, so soil will give an upward force. If this is the settlement Z, if the the foundation moves in the downward direction Z, okay, so the soil will give an upward force. So what will be that force? That will be Cu, the coefficient of elastic uniform compression, into the area of the foundation into the compression whatever is there. So kz, so we have kz into z, so that is the force. So kz is equal to cu into a, so that is into z. Okay, so that is the force. So if we consider downward forces to be positive, so that will be negative. Of course, positive, negative we will come later on. All right, so first of all is that force. Then second force is now, so second force is here, this block it moves in the x naught direction. Okay, so when it moves in the x naught direction, we have kx into x naught in the opposite direction. In the opposite direction. Okay, k naught into x, kx into x naught. So kx is, again we know kx is equal to c tau into a. Okay, c tau into a. So c tau into a into x naught. So that is the force in the x direction. Okay, so now, so we have the force which So if this is the displacement is z, we have the upward force cu a into z. If x naught is the displacement in this direction, we have the force c tau a into x naught. Okay, this is two forces. Then now considering the moment. Okay, so the CG is displaced from this position to this position, so we have to find out what is the total displacement. Okay, so we can neglect this amount, so we will consider the CG to be here. Alright, so if phi is very small, so we can consider the CG to be moved here. So x naught, so what is the total displacement? So it is x naught plus no total displacement, we let us consider it is x. Okay, we consider it to be x. Okay, so yeah, so x will be, so this is x naught, so x will be total displacement, x will be x naught plus this L phi. Okay, so this is L and this is phi, so this is L phi, this component will be L phi and this amount will be x naught, so x will be x naught plus L phi. Okay, so here what we can write is, so x naught is equal to x minus L phi. So here we can replace that x naught as c tau a into x minus L phi. Okay, so that is the force. So that is the horizontal force. Now let us consider the moments. Now the moments will have to be considered about the CG of the foundation, I mean the block foundation. Okay, it has to be considered about the CG of the block foundation because we have to consider the rotational equilibrium. So first of all, let us consider this force. So this force is uniformly distributed and it will be acting through the CG. Okay, now what about this force? So this force will be acting at this position here in this manner. Okay, so at a distance L. So we have c tau a into x minus L phi. So in this position x, this force, and we have the lever arm L. Okay, so the moment of this force about this point, alright, so we can write that as suppose moment of shear force about y-axis, so m tau y. Okay, so that we can write it as in this manner, so that will be equal to c tau a x minus L phi into L. Okay, so x minus L phi. Okay, so that is one moment. So moment from the force in the z-axis will be 0. Moment about this shear forces about the CG will be this much. Now again, what is the moment about of the soil resistance? Alright, so soil resistance will apply a moment. So that we have already found out. Just now we have found out. So it is equal to C phi I. Okay, so that is equal to C phi I. C phi into I, sorry. Okay, So this force, that is, okay, this force, moment of resistance. Okay, we have just now found out. So that is another moment here. So we have the moment of resistance of the soil. We have C phi, so coefficient of non-uniform compression, into the angle of rotation into the area moment of inertia of the base foundation. So apart from that, so these are the forces which are from the soil and the moments which are from the soil. Okay, so apart from that, we have the moment due to the displacement of the CG. Okay, so that is one moment we have. So we have mcg, which is equal to W into L phi. Okay, so this is the lever arm which will cause the moment, not this. So this x naught. This x naught is sliding displacement. Okay, so if I consider x naught in the mcg, then I will also have to consider x naught in this moment of resistance here. Alright, so that will be actually negated by the soil resistance, so we need not consider that moment. So whatever moment is coming due to the rotation of the CG from the vertical axis through the point O, so that we will consider for the moment for the displacement of the CG about this axis, that is axis to the point O. Okay, so that is the rotation here. So that is one moment. Then apart from that, we will have the applied force. So Pz we have, so Pz is equal to Pzt, that is, so that is Pz into sine omega t, one function we have. Then similarly we have the Px. Alright, then we have the moment M y, okay, in this case about the y-axis. Okay, so the forces are listed down. Let us list it again so quickly. So we have the force from this compression, so C U A into Z, that is this one. Number 2 is this one. Okay, so that is C tau A into X minus L phi. Okay, so that is this force. Then apart from that, we have the moments of the forces. So the moments of this one, so M, just now we have written here, so M tau y, so M tau y, so moment of this force, so moment of this force about the CG, okay, about the CG. So we have M tau y is equal to C tau A X minus L phi into L. So that is m tau y. Then obviously this force will be through the CG, so there will be no moment for the force in the z direction. Apart from that, we have the moment of, the soil resistance, moment from the soil resistance. So we have mr is equal to c phi into angle of rotation into the area moment of inertia of the base foundation. Okay. Then apart from that, we have the moment due to the displacement of the CG. So mCG is equal to W into L phi. So apart from that, we have the applied forces. So in the z direction, Pz sine omega t in the z direction. In the x direction, Px sine omega t in the x direction. And in the y axis, we have my sine omega t. So let us now sum up the forces in the z direction. So in the z direction we have Cu Az. So Cu Az minus P z sine omega t minus Pz sine omega t. So is equal to mass into acceleration in the z direction. So that is one, this one equation. So we can, so this is F is equal to ma. So we can, change the this one. So we can say, so m z, okay, mass into acceleration. So yeah, let it remain like that. Okay, so one equation we have. So similarly, we will have another equation in the x-axis. So similarly, we will have another equation in the x-axis. So we have this force. Okay, so C tau A x minus L phi. Okay, so C tau A x minus L phi. And what are the other forces? So we have minus Px sine omega t. So is equal to mass into acceleration in the x direction. Okay, so that is the force equilibrium along the x-axis. Okay, then apart from that, we have the movement. So now what are the movements? So let us see. So WL phi is in this direction, CA this is in this direction. Okay, so all clockwise. So if I consider my to be clockwise, okay, so we have the resistance from the soil, moment due to the resistance from the soil in the anti-clockwise. So this is anti-clockwise. Okay, so we can write, first of all let us write this one. So C tau A into x minus L phi into L plus, okay, plus WL5 plus WL5. Okay, so this is this one, this is due to the soil reaction, this one, okay, then minus this one, yeah, this plus this, okay, minus this, so minus C5 5 I, okay, so equal to, we have mass moment of inertia into the angular acceleration. So these are the equations for the forces in the z direction, x direction, and the moment about the y axis. Now if you consider this, if you see this equation, if you see this equation, then you can find out that there is no x, or no, there is no phi, so it is only z, z, and z. So this is an independent equation. So this mode of motion or mode of vibration is independent of whatever is happening here. Okay, so this we have already solved. So we have already solved that. So this is the solution here. So this will hold for this equation. Okay, then if you notice these two equations, so we have the phi in both equation. So in the force equation along the x-axis and the moment equation about the y-axis, so we have the variable phi, or the displacement, or the angular displacement phi, which is, affecting both the equation, both the motion. All right, similarly we will also have the displacement x, okay, in both the equations. So these two motion are interdependent. Okay, and in the next class we will solve for this equation quickly, and you can also try to solve. So the basic thing is, we need to find out what is the maximum amplitude, okay, in terms of x. So what is the maximum amplitude, capital X A, and what is the maximum amplitude of the angular motion phi A. So we have to find that out. Apart from that, we have to find out what is the frequency of vibration. Okay, so combined frequency of vibration. So that is what we have to find out. So that part we will cover in the next class. So I hope you have understood how to develop the equations, all right, and what are the motions to consider. Obviously, it is not very, easy to remember. Thing is that if you understand, then obviously things will automatically come out. All right. So first of all, understand the basic motion. What are the modes of motion? What are the modes of vibration? Once that is clear, you can then find out what are the forces and the moments which are acting there. Okay, so we will stop here and we will continue.